This section's the one that takes the longest because the problems will take you a little while to do each piece. Hopefully you've been, doing your homework along the way and studying along the way, because if you know how to do the stuff from previously, this stuff isn't so bad. Steps involved in optimization problems. So obviously you want to understand the problem. A lot of times drawing a diagram helps. Introducing notation. If you're talking about a volume, you're going to use V, things like that. So that's all that part's saying. And you want to express your whatever variable you're trying to deal with in terms of the other symbols or other variables. And you typically want, let's say you have your volume is x times y times z. You don't want to have this many variables going on. Okay, if you have this many variables going on, you can't really solve it. So maybe you know that y is double what x is. So instead of y, you would put like a 2x in that spot. Okay, you want to replace as much of the stuff as you can to minimize the number of variables you're dealing with. So that's what 5 says here. Okay, if it's expressed as a function of more than one variable, use the given information to find the relationships among these variables and eliminate all but one of the variables. And a lot of times writing the domain, a lot of times you don't actually have to write what the domain is, but you have to understand what the domain is. Okay, if you get a negative x value and you're talking about a length, that doesn't make sense, so you eliminate that as one of your solutions. And then find the absolute max or min values of your function using calculus. So do you guys remember how to do the max and mins? It's like what we've been doing before. So you find your slope, right, your derivative, and when it changes from increasing to decreasing or vice versa, right? When we're talking about absolute max and mins, can that occur at endpoints? Yeah, and that's where your domain comes in. If, it goes from 0 up to 10, you want to check 0 and you want to check 10 just to make sure that they're not the absolute max or min, okay? So let's look at, this is actually in the book, number 3. Find 2 positive numbers whose product is 100 and whose sum is a minimum. So we're trying to find the product is 100. So first you want to assign variables. Which variables do you guys want to use? X and y. So what would I write for this if the product is 100? X times y equals 100. So this is called our secondary equation. So our secondary equation would be x times y equals 100. And our primary equation is what we're trying to maximize or minimize. So we're trying to minimize the sum. So I'm going to write s equals. What would that equation look like? X plus y. And then I usually just write here whether I'm trying to maximize or minimize it, just so I don't forget what I'm trying to do. Ideas on what I can do. So if I want to minimize this, I'm going to want to take the derivative. But what do I want to do before I do that part? Okay, so what do you mean by that? Okay, so use this top equation. That secondary equation is only there, to substitute into the primary equation. So you can solve this for x or y. So let's say we solve it for, you guys care? I'll just solve it for y then. So what is y equal to? 100 over x. And then you would plug that in for the y here. So now you have a primary equation that's just in terms of x. So then we've got x plus, instead of y, we put 100 over x. And then think about how you can find a minimum. What would we do next? Take the derivative, and then what? You want to do the number line thing, right? So you're going to find when the derivative is 0, put those on the number line, and then try to find where it's increasing, decreasing, and then see if you can find the minimum. So I'm going to give you a couple minute head start on that. Right here. Okay, so working our way through here, taking the derivative, this would just be 1. And then here, you can think of this as a plus 100x to the negative first, if it's easier for you to take the derivative of that. So the derivative would be negative 100x to the negative second. Is that what you guys have? Now, you might want to write that as like just one fraction to find when it's 0. I think that's easier for a lot of people. So if I move that to the denominator and then I get a common denominator, what's going to be in the numerator? So if I want x squared in the denominator, I have to multiply by x squared up here. So I get x squared minus 100. Does that look okay to everyone? Okay, so then we find when it's 0. So the first derivative equals 0 when the numerator is 0. So when x squared minus 100 equals 0, or x squared equals 100. So what's x equal? Plus or minus 10. Now, if we read the question, it says find 2 positive numbers. So what can I eliminate here? I can eliminate the negative, right? So I'm just looking at when x is 10. So then we have to prove that there is a minimum there. We can't just say, oh, the minimum occurs here, because it could be a maximum, right? We're pretty sure it's one of those. So let's throw it onto a number line. So if I plug into the first derivative something less than 10, so let's say I plug it into this one here. If I plug in 5, positive or negative? Negative. Plug in 20 and I get positive. So that means that my sum is doing what here? It's decreasing until x is 10, and then it starts to increase, right? So that makes this point a what? Minimum. And does it make it the absolute min? Not necessarily, right? But we know that there's a local min there. Now, are there really endpoints for this? No, right? So if it's decreasing and then it's increasing, it has to be the absolute min, doesn't it? If it's decreasing on the left, everything on the left of it is larger than it, right? And then if it's increasing on the right forever, there's no way that there's anything smaller. So the number line makes this a local min, but for this particular problem, that's going to be your absolute min. So let's make sure we answer the question. Find 2 positive numbers. So this is my x. My x is 10. How do I find the other number? I can plug it back in, and you're plugging back into the secondary equation. What would you get for y? 10. So x is 10 and y is 10. Now this seems like I justified it because I talked my way through it. You would have to write just a little bit more on this to actually justify your answer. What do you think you would have to write to justify it fully? So we have to prove that this is a minimum. So since, how do you guys want to go about this? Okay, so since S prime is okay, so a lot of people do that. On the AP test, they'll write since S prime is decreasing. S prime isn't decreasing, S prime is negative, right? So you can say since S prime is negative, and we'll just go from 0 to 10. 0. And S prime is positive. From 10 to what? Yeah, really just when x is greater than 10, right? So I suppose I could flip that. That probably makes more sense. So let's say when x is greater than 10, we know what? We know there's a minimum at x equals 10, right? How else could I word that instead of since s prime is negative, we could say since s is decreasing here and s is increasing over here, then we know that there's a minimum, okay? So you just have to be very careful about saying, a lot of people do that, they say s prime is decreasing. S prime is negative, so s is decreasing. Because if you mess that up on the AP test, you for sure won't get that justification point, so. All right, I'm going to give you guys a few minutes to start number 7. Okay, so we're trying to find the dimensions of a rectangle with perimeter 100. So that's going to be my what equation? Secondary, right? When they give you information like that, that's your secondary, whose area is as large as possible. So that's my primary is my area. So again, just use x and y again. I'm guessing most of you did. If the perimeter is 100, what's my secondary equation? Okay, so 100 equals, what's perimeter? 2x plus 2y, right? You have x plus y plus y, so we got 2x plus 2y. And then your primary equation is what you're trying to maximize or minimize. So my primary here is the area. What's the area? X times y. And are we trying to max or min? Max. So I'm just going to write max here to make sure I don't forget what I'm trying to do. Okay, what's the next step? Okay, I'm going to take this, I'm going to solve for either x or y. It's up to you which one. I guess I'll solve for y again. So to solve for y, you'd subtract the 2x. So you have 100 minus 2x over 2, which turns into what? Yeah, so if you do like the heart method or just divide them each by 2, you get 50 minus x. That look right to people? So I'm just going to plug that in here for y. So now my area in terms of x is x times 50 minus x. Does that look okay to everyone? Now let's talk about the domain for a second. What's going to be true about my x value here? What's the smallest my x can be? It could be smaller than 1, but it can't be 0, right? So my x has to be larger than 0. It can't equal 0. So I know I can't have, like 0 will not give me an area that's as large as possible, right? So I don't have to worry about plugging 0 in at the end. So my x has to be greater than 0, but it has to be less than how much? If you have a perimeter of 100, 50, right? Do you see how these won't be included though? Because if x was 0, you wouldn't have a rectangle. If x was 50, you wouldn't have a rectangle. So the endpoints in this case, I don't have to try to plug in to see if they're going to give me my max. It wouldn't make sense for these to give you your max. Okay, on occasion, you'll need to test your endpoints to see if they give you that. Okay, once you get to this point, what do we do? You take the derivative, right? And I'll show you the second derivative test this time because with polynomial type functions, it's almost quicker. But you can definitely still do the number line thing and show it that way. Okay, so I've got the first derivative would be 50 minus 2x. And then for the second derivative test, you're going to need the second derivative. So I'm just going to go ahead and do it now. What's the second derivative? Negative 2. What's true if the second derivative is negative? It's always what? Nope. Concave down, right? So the second derivative is less than 0. It's concave down all the time, right? If it's concave down, are you going to have a max or a min? There's going to be a max at that spot, okay? Now, are you always going to just end up with a number when you do the second derivative? No, sometimes you'll actually have a function. So what you would do is you take the first derivative and find when it's 0. So this equals 0 when the 50 is equal to the 2x, right? Or when this equals 0, I just added this over. So when x is 25, and then you take that x is 25 and plug it into the second derivative. Okay, if I find the second derivative at 25, it's negative 2, obviously, right? But if it was a function with an x here, you just find what it is. It's less than 0, so then you can say it's concave down. There's going to be a max at that spot. Okay, so there's a max at x equals 25. Sometimes the second derivative test is just way quicker than doing the number line and showing this and writing all of this. So then we get to trying to find the answer, find the dimensions. So there's a max when x is 25. How do I find my y? You go back up to your secondary, right? And my secondary, you can plug into this one if you want to, but I already solved for what y equals. Y is 50 minus x, so what is my y? 25, right? So x is 25, so your y is 25. So your dimensions would be 25, I think it's in meters. Yep. By 25 meters. So when it's a square, you'd have your maximum. Questions on that one? So getting your secondary equation is obviously pretty important. The secondary equation is going to deal with the volume, right? And the volume is 10. And we're kind of given this picture here. If you weren't given the picture, obviously, you could sketch that. So the length of its base is twice the width. So a lot of people go, oh, x and y and z, that's great, but what do you know about this piece here? It's twice what this was, right? So if this is x, I would just call this one down here 2x. That eliminates one of your variables right away. Do you guys see that? And then this here, we can still call that y. Usually people stick with the x's and y's, so, but you can call it whatever variable you want. Okay, so length of its base is twice the width. We've used that, so we're good there. Material for the base costs this much, material for the sides and top costs this much. Find the cost. So our cost is our primary equation. So let's start with our secondary. Okay, so our secondary equation says the volume is 10. So if our volume is 10, we know 10 is equal to what? We multiply this times this times this, right? So 2x times y would give me 2x squared y. Now, is that going to be easier to solve for x or for y? Y. So that one I would solve for y equals. And if you solve for y equals, you're dividing by the 2x squared, so what do you get that's simplified? So we get 10 over 2x squared. Isn't that the same as 5 over x squared? Is everyone okay with that part? Okay, that's what you're going to plug into your primary. So let's come up with our primary up here. Okay, primary is my cost function. So if we're thinking about the cost of this, it says the base is $10 per square meter. So how many square meters do I have on this base? Square meters would just be your area, right? So 2x times x would give me 2x squared. How much does it cost for each of those? 10. So you're going to have 10 times your 2x squared. I'll clean it up in the next step. Everyone see where that comes from? Now, how much does this top cost? Same thing. Or no, not the same. How much does the top cost? 6. And the area is the same, right? So you see the sides and top are $6. So it's $6 for the top, and that would also be a 2x squared. Okay, and then each of the sides, so let's do the right side here. What would be the area of that? X times y, and that cost 6. Don't we have another one of those over here? So if we have another 6xy, isn't that just 2 of them? Or you could write 12xy. We'll clean it up in the next step. Okay, and then the front and the back. Okay, the front, the area here is what? 2x times y, and the cost is 6. That one's way too thin. Whatever. Okay, so we've got $6 for the 2xy, and then how many of those do I have? I have the front and I have the back, right? Okay, so let's clean up the cost here, and then we'll plug our secondary in. So our cost here would be 20x squared plus 12x squared, and we can combine those in the next step, plus, is this 12xy, and what's the other one? 24xy. And I would combine those together before I actually plug it in, just to get it as clean as possible. So I have a total of 32x squared and 36xy. And then you're going to plug this in for the y and solve. So my cost in terms of x is 32x squared plus 36x, and instead of y, we put this in there. What's 36 times 5? 180, right? So I've got 180 x to what power? Negative first. Or you could have divided by x. It's just easier for a lot of people with the derivative there. Questions on that? Okay, then the process is the same. Once you get to this spot, what do we do next? Take the derivative, right? So if I take the derivative, I get 64x minus 180x to the negative second. So that's the same as 180 over x squared. And then I would probably get a common denominator here. So my common denominator would be x squared. So this one you multiply by x squared on top and bottom, and you get 64x to the what? Third, good. minus 180. Once you have the first derivative, what do? Set it to 0, right? Okay, so it equals 0 when the numerator is 0, so the 64x cubed would be equal to 180. Go ahead and solve for what your x is there then. And then you can decide whether you want to do the number line or if you want to do the second derivative test. Either way is completely fine. I would probably choose the second derivative test because I think it's typically quicker. But I know it's new to you, so if you feel comfortable with that number line, just do the number line. If I just do this quick without actually solving it, I'm going to get x is equal to 180 over 64, and it's the cubed root of that, right? So that's the number you should have. I think that's just a ugly decimal. And then you want to show that this is going to minimize my costs, so you can do the number line or the second derivative test. Once you know that, to answer the question, find the cost. How would I find the cost once I know that that's a minimum? You plug it into the cost. Okay, your cost is this equation right here, isn't it? So you would plug this back into the cost, but you have to prove that it's a min, which we went over in the first two problems. So do you guys have any questions on how to finish that one? Okay. Take the last couple minutes to finish that up.